Lecture number 20, EE211, analog circuit design. So we have studied various things of differential amplifier in previous lecture. We know what is differential amplifier is. Differential amplifier is the one where we are giving input with 180-degree phase shifted, and on top of some common mode will take care of the transistor in saturation mode so that you can have the amplification. And moreover, we also learn on top of the differential amplifiers advantage, we learn how to find out the differential gain, and we also learn what is a common mode gain. Right, but all these things are happening on only one principle, or you can say that one assumption, that when you are taking the differential or the fully differential circuit, you have two balanced networks which are identical to each other, balanced networks. So both are exactly identical. Balanced network number 1 and balanced network number 2, both are identical. And the input which you are giving, one side it's V in, and another side you might have 180-degree phase shifted input. Along with that, there might be some common mode voltage, and accordingly you have two outputs, V out plus and V out minus. When you are taking the difference of these two, it's a differential amplifier. But this kind of amplifier is actually a pseudo differential amplifier where there are no relation between these two balanced networks. However, when you are connecting these two with some point, with some current, this makes sure that the common mode voltage is not going to affect these two balanced networks in terms of current determination. However, the current is depending on the tail current which is applied over here. Similarly, like if you are using the NMOS, like if you are using NMOS transistor, then such kind of configuration you are going to use. In case of pMOS, you are going to use the source current source rather than the current sink over here. So that might be like change, and you have to look at that accordingly. Now, one more thing, when we are doing this, as I told you, like these two circuits are exactly identical. It's a copy paste of each other. And yeah, when you are doing this, we also learn that this particular node, which is known as VP, is going to be equal to 0 when we are applying two signals. One is plus V in and another one is minus V in. Then this is 0, which we are calling AC virtual ground. Right, but in the case of but by the way, this is known as differential analysis, or in the case of common mode analysis, when these two signals are not there, and in the presence of common mode, both the circuits are like both the inputs are shorted to the same common mode voltage. In that case, VP is not 0. However, V out plus and V out minus is most likelihood that both are equal and they are getting shorted to each other, and you can find out the gain with a small, like say, combining both the circuits. Whereas in the case of differential analysis, we were finding out the differential gain from one of the part of the circuit, one of the balanced network. It's known as the half circuit analysis approach. So we studied all these things, and we also found out and we practiced some of the circuits. But what if it is not equal? Means, when I'm saying that not equal, means balanced networks are not exactly identical, and that's most likely happen also, right? So you cannot guarantee that both the transistors exactly identical. You cannot guarantee all the resistance, all the capacitors which you are keeping in the circuits at both the side, although it looks good on the paper. However, in reality, there might be some delta change. and that's the main reason why people use Monte Carlo analysis or statistical mismatch analysis with at least like in industry people are using at least 10,000 number of runs. When they are doing this, that means that if you are targeting some specifications like gain, bandwidth, or phase margin or anything, so one of them will be taken, and for 10,000 runs it's going to be checked for Monte Carlo results. So here the number of occurrences will be there when you are running the Monte Carlo, also known as the statistical mismatch analysis. So in that case, the output will look like this one. Like for different occurrences, you're going to see that output is actually from some range. It is there where there'll be some mean value, there'll be some standard deviation of sigma. So this is sigma. You might have you might be interested in 3 sigma, but some of the places like industry which are claiming for 6 sigma, they generally look at that whether my design designed amplifier or any circuit, whether it's matching with the 6 sigma or not, or it's not failing on any of the run. So generally this looks Gaussian because when you are doing this with different two kinds of things, one is the transistor mismatch. Sometimes they have process mismatch, and sometimes both. Like, so if you are doing according like transistor process mismatch, accordingly you will have the answer. But when they are doing this at the back, they are changing the GM or threshold voltage, all these things in a Gaussian ways. That's why you are going to have the the distribution with respect to the number of occurrences in terms of Gaussian way. So such things you are going to see just to make sure that it's working. So I'm giving you one example which needs to be taken by you. It's actually given in Behzad Razavi, the, the blue colored book, which is CMOS analog IC design. So you can read this book where this is already given. If it is mismatch and I'm doing the common mode analysis, if you remember, the common mode analysis is the one where both the balanced networks which we were expecting to have exactly same, but in this case I'm saying it's not. RD is not exactly equal. One side it's RD and one side some delta change is there. However, M1 and M2 are exactly equal. What I mean to say for the exactly equal means GM1 equal to GM2 equal to, let's call it GM1. Whereas RD, like the left side of RD and the right side of RD are not exactly identical and there is some mismatch. In that case, you can say that V out 1 and V out 2 are not equal. If they are not equal, they are going to have, they are not going to be short circuited, but you have to take care of them separately. And notably, the current flowing through this one and this one are known to us because the current flowing through these one are actually depending on, as both of them are equal, it's depending on the current which is Gm by 1 plus 2 Gm RSS. By the way, RSS is the resistance of the current sink. So from this you can find out that there is something is going on. This is the current which is actually going to, so input common mode times this one is going to give you the current, right? And that is going to impact value across these resistances. So if you're writing v out 1 and v out 2, you're going to see that this v out 1 and v out 2, which are actually the small delta change, I can write down from this current that is equal to nothing but gm by 1 plus 2 gm rss, which is flowing through this one. Both the transistors are identical and whose uh, transconductance is gm. So you can write down this one very very easily. And if you wish to find out the vp voltage, it's also very simple to find out. Note that gm1 plus gm2 is nothing but 2 gm, or both are identical to each other. So in that case it's 2 gm. So in that case, from one side it's flowing from 1 gm, and another side is like another gm. And if you're writing down in terms of delta vx and delta vy, you can have these equations, which is already known to us how to find out, because you need to find out across rd, right? So when you're doing this, you have two different values at this node and this node. They have to be subtracted, right? So such kind of signals, where such kind of situation where the input is input common mode and the signal which are available are actually differential because of the presence of mismatch. That mismatch might be between m1 and m2 also. That mismatch might be between rd and transistors together also. All these things can happen together or maybe separately. So in that case you need to separate both the analysis and you need to find out the exact value accordingly, and you need to find out the value. In this case, this kind of gain is not known as just a common mode gain, it's known as common mode to differential mode gain, because you are giving the input which is common to both, but output side you are taking the difference of these two, so this is becoming differential mode output. Okay, if you understand this, and like you can work upon it, and you can find out more things which are given already in book, which will give you more insight, and there are some examples are also given. So effect of common mode noise in presence of mismatch. When we are saying mismatch, you can observe, look, this proves that, like in earlier case when we are saying that both sides are exactly equal and opposite in differential mode, and in common mode both are equal. If both are equal, then there is no common mode noise. But as these two balanced networks are not identical, in that case common mode will be there, or you can say that whatever the noise was here, it will be accordingly transferred, and that will be reflected over the output. So that has to be taken into account, and that is what generally happens. And that's how, when there is a mismatch, you can say that there are some common mode noise because they are not identical. And as both the sides are not equal, but in the case of m1 and m2, if you are giving this, the differential one will also not have the same amplitude. So in that case even harmonics are also not zero. So this is what going to happen when both the balanced networks are not equal. What I'm saying next is, let's find out the common mode rejection ratio. Notably here the common mode rejection ratio is poor, of course, right? Because you will have some common mode noise, you will have some even harmonics, and like even though you have very good differential mode noise, differential gain, common mode gain is also very high. So the overall performance wise, your CMRR will be degraded, or the higher value cannot be achieved. So now let's look at the possible thing when, look at this, the circuit which I am giving right now here is, it does it it has actually everything identical, means this balanced network 1 and this balanced network 2 are equal and identical. What I mean to say is M5 is equal to M6, let's call it M5. M3 is equal to M4, let's call it M3. M1 and M2 are identical and let's call it M1. When I saying this, it's like GM and ROs are actually matching one. And as this is for CMRR, we need differential gain divided by common mode gain. We need to find out its value. So if we find out the absolute value of the differential gain rather than writing in mod, when we are applying the differential mode, you remember you have to use the theory which we have started with. Both the balanced networks are connected with a wire, and whatever is connected here, you can say that Vp is equal to 0. Let's call this one as Vp. It's an AC virtual ground. Okay, so in that case you can find out the gain from one side, and you can declare that one as your differential gain. So one side you can find out, which is like that. By the way, this is Vp point, this is M1, this is V in, and this one is V bias 1, and this one is the point where you are taking V out, right? So in that case it's equal to nothing but, okay, moreover this R1 resistance will be changed as follows: R1 and R1, sorry, R1 by 2 and R1 by 2, and this is connected to X point, this is connected to Y point. If this is like, these two are the identical balanced networks, and both side, one, this side is X and another side is, you can call it as, it's Y, but Y is equal to minus X. So in that case the midpoint which is connected by two boxes has to be grounded, or you can say that this is also AC virtual ground. So you can, like, you can take one this side and you can avoid another one, right? Just in case of finding out the differential gain. So using this you can find out the differential gain as follows: it's equal to minus gm1 times gm1 times what is the output impedance. You need to find out that. So this is M5, this is M3, right? So, and along with that you can see from here. So first of all, this is, by the way, cascode. You can start from here. This side it's RO1, this side R1 by 2. So in total this side it's RO1 in shunt with R1 by 2, and looking from here you are going to see GM3 RO3 times RO1 in shunt with R1 by 2, and looking upside it's a diode connected load, so it will be 1 by GM5, right? Notably you can write down the whole thing over here: GM3 times RO3 times RO1 in shunt with R1 by 2 and in shunt with 1 by GM5. So that's the differential gain for this circuit, right? Now we might be interested in the common mode when both the networks are identical. In that case this is not AC virtual ground, and what is going to happen? First of all, as this is not ground, so you can draw the equivalent circuit over here. Let's call it M7. Let's call it VB, right? On top of that, you might have M1, and look at this, X and Y are exactly same value, so this will be shorted. Let's remove this balance network. So X and Y are exactly same, so both will be shorted. V out are also same, so both are shorted, right? When you're doing this, there is no role of R1 at all, and here two M1s are in parallel, so let's call this one as M1 plus M2, right? And as both are identical, let's call it 2M1 are there, or for better purpose we can do this one also, whichever you like, you can do it. This is M1 and this is M1. Other than that, it's like both the M3 are in parallel. Let's call this one as VB, let's call this one as V in, and here it's a diode connected, so we can replace this for simplicity. By the way, both sides are actually 1 by 2 GM5, right? Because 1 by GM5 plus 1 by GM5 is going to give you, sorry, so 1 by GM5 in shunt with 1 by GM5 is going to give you 2 by GM5 plus divide by 1 by GM5 plus 1 by GM5. Sorry, there is one mistake. It has to be 2 by GM5 square, and this is going to give you 1 by 2 GM5, right? So as I wrote earlier, it's 1 by 2 GM5, which is very simple one. Okay, now this is the V out we are taking, right? In the case of, first of all, writing the common mode gain with our practice, so if you're writing on absolute scale, it's minus 1 by GM1, sorry, 2 GM1, because 2 GMs are there, and plus RO7. Looking from here, that side, it's a source degeneration, so this is going to be there. And looking from this side, where it's changed by M3 plus M3 to M3, let's call this one also 2M1 are there. So in that case, looking from here, it's a big cascade, triple cascade is there. So you can write down this one starting from here. It's G2 GM3 times RO3 by 2, because that's getting half. So this is going times GM1 times RO1, I'm removing 2, and times RO7 in shunt with 1 by 2 GM5. Of course 2 GM5 will be winning, so 2 GM5 will go there, and you can write down the common mode gain directly, right? And differential gain also, like GM5 might be winning quantity, so you can write down directly the gain is minus GM1 divided by GM5, and common mode gain is minus, so this becomes 1 by 2 GM5 times 1 by 2 GM1 plus RO7, and the common mode rejection ratio is going to be equal to, so by the way this is approximated and I'm taking, so mod will give the plus sign, by the way, both the quantities. So CMRR is going to be equal to nothing but GM1 divided by GM5 times 1 by GM2 GM5 times 1 by 2 GM1 plus RO7. GM5 is gone, so it's going to be equal to 2 GM1 times 1 by 2 GM1 plus RO7. You can simplify more and you can find out this one is 1 plus 2 GM1 RO7, right? So the unit wise it's unitless, so this approximated value is correct. So you can further do the analysis and you can find out CMRR for any circuit, anything, right? So just you need to apply what we have learned. Now going into the next part of the understanding, which is the common mode range, or we also call it CMR. It might be either input common mode range or the output common mode range. We are going to study that. By the way, input common mode range and the output common mode range are measured at input and output respectively. The role of input and output common mode range is going to make sure that the what value of common mode value is required, just to make sure that all the required transistors are in saturation, so that we can use it as an amplifier. So this is our role, to do all these things. Now what I'm using as an example is having the pMOS input. As I was explaining you earlier, that if you have the differential circuit which has the pMOS input, you might not have the current sink, but you are going to have the current source. So these two are the identical balanced network. They are connected with a with some wire. Then this becomes VP as AC virtual ground when you are the applying the differential inputs. Notably, what we are doing is the common mode analysis. In that case, we are giving the common mode input. We don't consider right now the input. So input means, I mean to say, differential inputs. So these are the small signal AC inputs where I wrote small v in and v in with the different sign. Over here it's minus v in and over here it's plus v in, right? So in that case I need to find out the common mode range. So we can start from here, where I'm interested in, let's assume that input common mode range. If I'm interested in input common mode range, what I'm going to do, I need to find out where the input has been applied. So I know the inputs are applied over here. First of all, you can see the previous circuits. Okay, the inputs are over here. Right now we are talking about the common mode input only, and the analysis which you are doing, it's DC analysis. Most of the time it's DC only, right? So it's DC analysis, as this is common mode, and make sure that your transistors is in saturation or not, or whatever the mode of operation you want, accordingly you can design it. But we are designing for the saturation mode of operation. So I know that the inputs are applied at transistors M1. By the way, there are two M1 transistors and both are identical to each other. So if I am applying here, the upside towards VDD is going to be known as max side, and looking at downside it's known as mean side. Okay, so after getting such kind of thing, we need to learn one more thing. We know that if this is a, a transistor where this is gate, this is source, and this is drain, this voltage is, by the way, VDS set. Some books are writing overdrive voltage also, and some people are writing V on voltage, right? So different books have different notation, but the meaning wise all are same, and they are saying that it has to be more than VGS minus VTH, where VGS is gate to source voltage and VTH is threshold voltage, right? This is already known to us, and notably this value has to be more than 250 millivolt. This is also known to us to make sure that your transistor is in saturation. So if this is the case, and let's assume that you are standing over here and you are holding a multimeter, plus sign connected over here, minus sign connected over here, you are going to observe VDS set. But if you are looking at other side, this side is VDS. However, from this side, I know that it has to be VGS minus VTH. If that is the case, VGS is already known to us. If this potential from here to here is VGS, then this potential has to be minus VTH, because those many voltage sources are coming in series. So here to here it has to be VTH, just to follow the KVL. So in total, from left side you can see it's VGS minus VTH. With respect to this one is plus terminal, and let's call it this one is plus terminal, and this one is minus terminal. So in that case, this side VGS minus VTH and other side is VDS set, or you can simply write down sometimes VDS also, right? And similar thing you can apply to pMOS side. Notably, pMOS is reverse, and the equation is also changed, because this equation does not becomes VGS minus VTH, but it's mod of VGS minus VTH. Sometimes people are writing VSG also, right, instead of VGS, because it's some higher to lower voltage you need to take care. So VSG will give you the positive number, whereas in the case of NMOS, this is going to give you positive number. After getting so much of understanding, what we can do, we can write down directly. If you are interested in, let's assume that I'm interested in finding out the ICM mean, or the input common mode minimum side. Minimum side is where the input is given. You need to go downside with respect to ground. So there is a big mistake over here in that case, because it's not VGS, but it's some different value. It has to be VTH. So that's the mistake over here. I made a mistake. That is a mistake, because here this is a source terminal, so do not go with these things. But yeah, if I'm going to write it down over here. So here across this one, it's going to be VDS2. Notably, VDS2 is a saturation voltage, right? And from here to here, it's, if this is VSG, this side it has to be VTH, right? So in that case, you can denote it as VTH1, because from here to here I'm expecting to have, right? Or you can write down VSG minus VTH, right? So in that case, it has to be like this. So in that case, this input side is not going to be equal to this one, but it's going to be equal to VTH1 plus VDS2, right? That's the minimum side. Both sides are identical, so both sides that much voltage is required. Notably, VDS2 is nothing but some value which is more than 250 millivolt, and VTH is technology dependent thing. Now that is the ICM at minimum side. Now if I am interested in finding out the ICM at maximum side, I need to see what is at the upside. If I'm interested in finding out what is at the upside, I can look at the transistor, and I need to look at the different voltage sources coming in series or in parallel. So the higher one will be winning if two are in parallel, but most of the time you will see that you will get the correct answer which you want. So here it's VDS3, and this is already VSG, but let's call it VSG1. So input common mode at max side, if I'm starting to look from here, what I'm going to see, I'm going to see following things. I'm going to see that I'm going to see that so VDD, and then there is some voltage, two voltages, and I am checking the voltage over here. By the way, this is VDS3 and this is VSG1. When I am checking with respect to ground, and this multimeter is in my hand, by the way. When I'm doing this, you need to apply a KVL. In that case, what is happening? It's equal to, you start from here, it's VDD minus VDS3 minus VSG1. You can make it in the reverse way also with mod value. So you can take it reverse also if you want, right? So you can have such voltage for minimum side and maximum side, and you can find out the input common mode minimum and maximum, right? As denoted here, there is a small mistake because this will not be VTH1, so do not follow this. This is wrong. It has to be VGS, sorry, VSG. From here to here it's VSG1. Now let's understand that now you are interested not only at the input side, but you are also interested at output common mode range. What value of common mode range I need to apply? So for that you need to go to the output side. Either of the side you can go and you can find out, because both are in parallel, so parallel voltages are going to be like, has to be equal. Like they have to make sure that from here to here the voltages are same, right? Because it's following the KVL. So and everything is identical, so everywhere uh, across each transistor the voltage will be same. So if I'm interested in finding out two things, output mean side, so mean side is with respect to ground and max side is from VDD to that particular node. So now let's find out that what is OCMR. So in that case OCM max has to be find out. OCM max is nothing but, if I am holding a multimeter in my hand and if I am measuring the voltage across M2, it's going to be VDS2. By the way, source is here. In this case, source is here. Okay, so VDS2, that's fine. But if I'm looking at OCM mean, as we have done last time, it's starting from VDD minus, I'm going to see here, again it's mod of VDS3, and from here it's again VDS1 mod of that, or you can write down VS. Okay, rather than writing this, it's going to VSD3 and this is VSD1. So VSD3 minus VSD1. Notably, when you are doing this, these VSD and VSD1 has to be like positive, and while doing this you will understand that these values has to be more than 250 millivolt. And if you are interested in finding out the OCM R or the ICMR, so ICMR, which is the main quantity, or the OCMR, which is the main quantity, then you have to subtract ICM max minus ICM mean. Similarly, for this case, it has to be subtracted from OCM max minus OCM mean. This is very much important in terms of finding out or keeping the transistor in saturation mode of operation to get the proper amplification. Now, okay, so this is already done, right? So common mode range determines the range of voltage for which the transistor is in saturation. ICMR is an allowable swing at the input side and OCMR is an allowable swing at the output side. So you can write it down or you can keep it somewhere in your understanding side. But now let's take one example and you need to find out ICMR and OCMR. So let's start with the ICMR. How this is. So this circuit is given to us. Notably, when we are doing the ICMR or OCMR analysis, it's a DC analysis, or also known as, it's a common mode analysis. So when this is happening, when it's DC or common mode analysis, this side is V common mode and this is also V common mode. These two are already known to us. This is M5, let's start from here, M1, M2, M3 and M3, and this side is M4, M4, right? So this is actually happening to us, that you need to find out input common mode and output common mode. So input common mode will start from here. You need to go upside, downside. Upside is going to give you ICM max, downside is going to give you ICM mean. These two are V out, so upside is giving OCM max and downside is going to give you OCM mean. The difference of these two is going to give us ICMR and OCMR. So let's start with the ICM max. ICM max is nothing but VDD minus VSD4 minus VDS3, and you have to look at this. This is actually going to be equal to plus VTH2, because VTH over here and here it's VGS, so VGS2 will be incorporated in the mean side. So ICM mean is equal to nothing but VGS2 plus VDS1. Notably, this VDS1 is nothing but 250 millivolt, and which will make sure that your transistor is in saturation. If you are taking the subtraction of these two quantities, which is going to give you ICMR, which is input common mode range. Now we might be interested in OCMR, which is nothing but OCM max minus OCM mean. So if you are interested in this, you can start from here. So this is nothing but VDD minus VSD4, which is going to be equal to OCM max. In the case of OCM mean, it's going to be equal to, you have to start from here. So it's equal to VDS3 minus VD plus VDS2 plus VDS1. Notably, all the all the voltages are going to be added as it's following the KVL. And in that case, when you are holding a multimeter in your hand, from this point to this point, all are going to be added. However, when we are going to make the OCMR in total, it's going to give us all the quantities with the negative number, because the negative is over here, and same is applied for ICM mean. You can write down one more time, which is VDS3 minus VDS2 and minus VDS1. So this is going to give you the ICMR and OCMR max and mean, right? And there is no role of this resistor, as it is between these two nodes, where actually it's going to be decided by the available voltage over here. Means it's depending on VDS2 plus VDS1, or you can say that it's depending on VDD minus VDS4 minus VDS3, right? So either of the side, you need to apply KVL just to manage all the energy conservation law. So thank you for today, and maybe we can talk more maybe next time with new new chapter called feedback. So thank you very much.